and welcome to the Evaporation and Intermolecular Forces lab procedure. Our objective for today, in this lab, our objective is to study temperature changes caused by the evaporation of several liquids and relate these changes to the strength of intermolecular forces of attraction. The materials we need: vernier lab quest with temperature probe already plugged in, filter paper cut into 2.5 by 2.5 squares, small rubber bands. We have a few over here, small red rubber bands, test tubes, test tube rack, and 4 liquids. We have water, which is actually in test tube C, ethanol in test tube B, acetic acid in test tube A, and acetone is in test tube D. We're not going to do isopropyl alcohol today. So our procedure, first thing we're going to do is plug in the vernier temperature probe to channel 1 of LabQuest 2. Done. Program your LabQuest 2 to collect data for a period of 180 seconds. Already done. 3, wrap the probe with a square of filter paper secured by small rubber bands. Take the filter paper, wrap the tip of the temperature probe with the filter paper. And secure with the rubber band. So we're going to measure the rate of evaporation of these 4 liquids. So what we're going to do is we're going to take the test tube. We're going to start off with the first one, which is water, which is actually letter C. So we're going to put that probe in there and just let it hang out. And the temperature is going to go down. And once it stops moving, we can start the procedure for this particular liquid. So if we go to the data table, we have water, which is C, ethanol, which is test tube B, acetic acid is A, acetone is D. Our initial temperature, we're going to pull the probe out once it stops moving. So at 23 degrees Celsius, 22.9. 22.8, that sounds like a good starting spot. 22.8 degrees Celsius. And I'm going to pull it out and click play at the same time. And click play. Play it over here. Discard previous data. And you're going to see it go down. So in 3 minutes, the graph should stop moving. And we'll record our final temperature. So as you can see, the temperature is decreasing. The water is evaporating from the filter paper. Just like when you sweat, you release liquids out of your pores. It's not the act of sweating that cools you down. It's when that sweat absorbs your body heat energy and evaporates. When it evaporates, it cools you down. Evaporation is an endothermic process. It takes in heat to evaporate. So it's taking heat away from your body, the sweat is. The sweat is taking heat away from your body and evaporating into the atmosphere. So you feel cooler. So right now we're at 20 degrees Celsius. Let's check the time. We're about a minute in and we've already dropped to 19.9. So about 3 degrees Celsius we've dropped. That's only after 1 minute. And also we can stop if we reach a low temperature and then it starts to climb up again. What we're really interested in is the lowest temperature. So yes, we have 3 minutes, 180 seconds programmed in, but if it goes down and then stops and starts climbing up again, we really want the lowest temperature. The reason for that is after all the liquid evaporates, the temperature is going to start rising because the temperature probe is going to be taking the temperature of the atmosphere, of the air around it. So we're at 18.9 degrees Celsius, and we're 100 seconds in, excuse me. So hovering around 19.0, 18.9, we're at 130 seconds in, so 150 more seconds, so less than 1 minute left. 18.9 we haven't moved from. 19.0. 18.8, we got 18.7 for a brief moment. We're at 160 seconds, so 20 more seconds. We're at 18.7. 170 seconds. We're still at 18.7. 177 seconds. And 180. So let's take a look. We're at 18.5 degrees Celsius. 18.5 degrees Celsius. So we'll calculate the change in a second. However, to get ready for our next liquid, ethanol, we are going to hold onto the rubber band. Let's see if we could do this without interfering with our numbers. So after this, we record the initial temperature and the final temperature, discard the used filter paper, save the rubber band. So we'll pull off the filter paper, save the rubber band, and wipe the tip of the temperature probe with a piece of paper towel. We'll set up the second trial, ethanol. Once again, take a clean piece of filter paper, wrap it around the tip of the probe, and I'm going to secure it with a brand new rubber band. I'm going to save the old rubber band for next year's experiment, but I am going to use a brand new rubber band to not interfere with any of the results. And then we put it into the ethanol, which is letter B. All right, it looks like our ethanol temperature leveled out at 22.3 degrees Celsius. So that is our initial temperature. Let's remove the probe and click play at the same time. And put the probe at the edge of the lab bench. Let's discard our old data. And we already dropped down to 20.3, 20.2. And we'll go again for 3 minutes. But we don't have to sit and wait for that to go for 3 minutes. We could do our calculations. So we have 22.8 as our initial. Our final is 18.5. Our change, we always do final minus initial, so it will be negative. 18.5 minus 22.8. Our change, we went down negative 4.3 degrees Celsius. Started at 22.8, we went down, so our temperature change is negative 4.3 degrees Celsius. So now for ethanol, we're at 15.3. That is after 53 seconds. So once again, we will look at the temperature. We want the lowest temperature, so if it starts to creep back up, then we can stop our timer early. We're at 14.3, 14.2, 14.2 again. Now fluctuating around, I saw 13.9, 14.0, 13.9. Seems like we're leveling off. We're probably close. So we're 90 seconds, about halfway through our timer. 13.7. 13.6. 13.5 for a second. We're at 125 seconds, 13.4 degrees Celsius. So you have 50 seconds left. $13.1. 30 seconds left. 12.9, 12.8, 12.6, So back up to 12.9. See how much time we have left. 10 seconds left. We're at 13.0, 12.9. 5 seconds, 4, 3, 2, 1, and 13.0 is what I saw last, 13.0 degrees Celsius. 13.0 degrees Celsius is our final. So next, we have acetic acid, which is letter D. So we will take the filter paper, clean piece of filter paper, wrap the tip of the probe with the clean piece of filter paper. Take a brand new rubber band, secure the filter paper tightly to the edge of the probe. Stick it into test tube D, and we'll wait for the temperature to normalize. Now, if you're watching at home, please make note that the acetic acid is in test tube D, and the acetone is in test tube letter A. So please make that change. It should not affect your results, but we do want to have everything correct. So we're at 23.8, probably should get somewhere between 22.8 and 22.3. That seems to be the room temperature right now. 23.3. You can always clean up the area while you wait. 23.1, we'll give it a couple seconds, see if it changes. 23.1. 23.0. 22.9. That seems like a good place to start off with. 22.9. Let's see if it goes down one more tenth of a degree. All right, 22.9. We'll remove it from the probe from the test tube. Click play. Discard all data. And place the probe at the edge of the lab bench. So we already dropped down to 22.6, 22.4. But while we wait, we don't have to sit and wait for 3 minutes. We can do the subtraction from before. For ethanol, 13.0 was our final minus initial, 13.0 minus 22.3. Which will give us a negative, once again, temperature went down, negative 9.3 degrees Celsius. So for water, we went from 22.8 to 18.5 for a change of negative 4.3. Ethanol had a greater change from 22.3 to 13 for negative 9.3 degrees Celsius. Acetic acid, we started at 22.9, and after, let's see how much time, 60 seconds, we're at 1 minute, we went down to 20.5. So we have 2 more minutes. After 2 minutes, we will record the temperature. Remember, we want the lowest temperature, so if it starts climbing back up, we can stop a little bit early. .9 after 100 seconds. So we got 1 minute and 20 seconds left. 19.6. So remember, we're measuring temperature change to rank these substances on intermolecular forces. The greater the temperature change, the weaker the intermolecular force. And we'll talk about why that is in a little bit. We're at 130 seconds, so we have 50 seconds left. So keep that in mind. The greater the temperature change, the weaker the intermolecular forces. We're at 147 seconds, so we have 150 seconds, about 30 seconds left. We are at 19.1, 19.2. 19.2, 19.3. At 170 seconds, 19.2-ish, 19.3. We're at 19.4. Oh, we just ended, and we're at 19.2. That was our lowest point anyway, 19.2 degrees Celsius. All right, so for our last one, let's remove the rubber band and the filter paper. Put this aside. It's on nice and tight. A little slippery. Okay, also we'll dry off the probe. And put one more piece of filter paper on. And we'll do our final liquid, which is acetone, which is in test tube A. Secure it tightly with a brand new rubber band. And place it in the test tube. So putting in test tube A. I just saw the rubber band break. So we're going to have to be very careful when we're pulling the probe out to not lose the filter paper. And we'll wait for the temperature to normalize. So before we were talking about intermolecular forces, and the greater the temperature change, the weaker the intermolecular forces. Think about what's happening. We're pulling the probe out of the liquid, and the filter paper is saturated with that liquid, either water, ethanol, acetic acid, or acetone. Just like we talked about before, you sweat not to cool you down when you sweat, you actually cool down when that sweat, that liquid, absorbs heat from your body and evaporates. That evaporation is an endothermic process. It takes heat away with it. So, the stronger the intermolecular forces are, the stronger the attraction is between the molecules, whether it's water, ethanol, acetic acid, or acetone. So, the stronger the intermolecular forces, the stronger the attraction is. That means it'll be harder for that liquid to turn into a gas. Remember, a gas is a freely moving particle where liquids are sliding and touching. So in order for a liquid to turn into a gas, it has to break free from that sliding motion and go into free movement in random constant straight line motions. So the easier it is to evaporate that liquid, the weaker the attraction, the weaker the intermolecular force. So let's take a look. We're at 22.9. Perfect. That's exactly where we were with the acetone. Be very careful when you're pulling it out. Try not to lose the filter paper. Click play quickly and discard, cancel. Click play quickly. This one is going to probably not be the whole 3 minutes. But let's see where we are. We're already at 18.4. Secure it to the end of the table so we don't lose the filter paper. Use the little paper towels. Hold it up. 14.4, 14.2, 14 even, 13.9. Remember, our lowest number was the ethanol at 13 degrees Celsius. 13.2, 12.9, so now we have the lowest temperature out of any of the 4 liquids. 12.3, 12.2. We're only 50 seconds in and we're at 12 degrees Celsius even. 11.9, 11.8, 11.7, 11.6, we just reached the 1 minute mark. 11.6, 11.7, 11.8, 12, 12.1. So now we're starting to go back up. So if you remember, our lowest temperature was 11.6 degrees Celsius. So that was so quick we couldn't even calculate for ethanol. So now the temperature's going up. Now we're 13, 13.2, 13.4. And let's take a look at the filter paper. The filter paper is completely dry. All of the acetone evaporated, and that's why the temperature is starting to climb. So now there's no filter paper on the probe, and we're at 15.2, and it's going to climb back up to room temperature. So we can put that aside. Let's do our final calculations. So we have final minus initial for ethanol, 19.2 minus 22.9 is negative 3.7 degrees Celsius. And finally, 11.6 minus 22.9, that's going to give us a negative 11.3 degrees Celsius temperature change. So, acetic acid had our smallest temperature change, and acetone had our largest temperature change. Thank you for joining the Evaporation and Intermolecular Forces lab procedure. I hope you learned something today. Please join us again soon.